I think we are going. So let's take some time to first, because I understand it sounded to me like the general concerns were broad conceptual concerns, not necessarily that specifics are going too fast. So this can just be a discussion. So I know it's tough to just ask the question, what are the broad conceptual concerns, but I'm just going to do that anyway. Do people feel, so we've talked in particular about understanding first order differential systems. First order being derivatives, single derivatives, x with a single dot that are linear. That was sort of prior to this week. Linear being that the entire system can be described as a first order derivative equals a matrix times a variable. Okay? And we talked about how we can look at the properties of the eigenvalues of that matrix, and it will tell us something about the nature of how the solutions of the variables evolve in time. And then there's sort of a mapping, right? If they're imaginary, they oscillate, if they're big, they explode, etc. So, of everything I've said thus far, are there any major conceptual concerns? Yeah.
I think one thing that I'm a little bit thinking about is the eigenvectors and eigenvalues and how you now use them in the dynamics.
Great. Okay, perfect. Great question. So, this is a tricky question. There's maybe some reasons why this hasn't been explicitly clear, and it's because there aren't, in some sense, the rule is, as we've described it, purely qualitative. We have said if the solutions have components that are imaginary, or if they do not, the solution oscillates or it does not. And those are the eigenvalues, not the eigenvectors. So we've looked primarily at the eigenvalues of the matrix. We have also looked a little bit at the eigenvectors of the matrix. However, as I sort of pointed out on Tuesday, those eigenvectors, so the eigenvalues are interpretable because we can just look, are they real or are they not? Are they positive or are they negative? And then we know what our solution does. That's eigenvalues. Eigenvectors, sometimes we can plot them. Now, if there was an imaginary eigenvalue, it's hard to plot it on a 2D plot. We're looking at a 2D system. So we've really only considered solutions to that when the eigenvalues are real. And if we plot then the eigenvectors, which is sort of a smaller section of problems that we've looked at, we can demonstrate that the dynamics, the solution to those dynamics move directly along those lines, the lines of the eigenvectors. And that's sort of all of the concepts, basically, surrounding our first order linear systems. Okay? And on Tuesday we went into first order non-linear systems and a little bit of second order systems. But all we said about higher order was you can rearrange terms and make them first order. So conceptually, they're the same. Just change your variables. Okay? So I want to still pause and give you guys another chance to ask any other conceptual questions about everything I just sort of said.
Or any other questions about anything?
At all? Yeah.
This isn't really a important question, but could you explain how what you just said relates to sort of how we introduce this whole concept of where you have the derivative of something in respect to time and we're trying to get the population over time?
So we are going from an equation that is a derivative. That's basically it. What I've said conceptually now in math form. This, for the most part for us, has been two-dimensional, though it could be higher dimensional. And all you guys have to worry about if it's higher dimensional is saying something qualitative about the solutions. Like if even one of them is positive, it's unstable, for example. But for the most part, we're considering this in a two-dimensional setting. And we can then write a description. If we end up, well, how much detail do I want to go in right now? If we end up rewriting this in our diagonalized form, I called that prime. And then we had something like V diagonal v, there's an inverse here, x prime. I now have a solution I can write for each one of those variables in time. So these are both vectors. I think, yes, last time I noted the fact that they were vectors with a tilde. And because these are diagonal, I can actually break this system up. And, well, I don't know if we've had I don't know if you've had to actually write out the solutions. I mean, we have the way we've thought about it in this class is we said we start at a point, and then we estimate the derivative at that point, and then we take a step in that direction according to that little estimate. And that describes how x evolves in time. Well, each variable evolves in time. That is a numerical answer to how we get x of t and comma y of t. We don't have, people were confusing this. People were confusing the terminology of numerical and analytical. Part of the problem that we have in describing these systems is it's hard to come up with an analytical solution. I can't just write x of t equals some function of t. Actually, we can go with these solutions, but conceptually right now. So the way we've dealt with this is what we've illustrated as this forward Euler method, which was a numerical method to take t at some initial point, to estimate how much it changes, to step in that direction, and to do the process again and again and again. As long as my estimates were small enough, that's a very good description of how x moves in times and y moves in times, and just for completion, I'm defining x tilde as, I'm defining x tilde as a vector of x, y, two-dimensional.
Wait, so this is probably a tough question, but how does that Euler approximation relate to the x dot equals mx?
Well, so all I've done is rewritten the x dot equals mx in two different ways. You can think of this in either way. Let's just think of x dot equals mx. Okay, don't think about the diagonalization. I was going somewhere.
No, not about the diagonal. Like my question is, how does x of t relate to
Perfect.
x dot equals mx?
So all I do to do a numerical simulation here is I pick an initial x and y. Right? If I pick an initial x and y, I can plug those into values here. I can multiply that by the matrix, and then I get how much x and y change. Okay? Then I use how much it changes to take a tiny step, and then I get a new x of y. Plug that in here, figure out how much it changes on the next time step. Repeat the process again, and again, and again, and in Julia, the simulation then evolves in time, starting at some initial point.
Wait, but how do you do very specifically with each time step when you're so you multiply it, but like how long is each time step when you multiply x by that?
So that was, I think, before Thanksgiving, we talked about that dt being a choice, a parameter choice in the simulation. We make it really small. Ideally, it should be infinitely small, but of course that would take infinitely long to run on a computer. But all we're doing is taking x of t, taking some initial guess, figuring out how much it changes, and then taking our next estimate in time
Okay, I get it.
by multiplying it by dt times how much it changes.
Yeah.
There you go. Carlos says
Maybe
something to
maybe
add.
we just write out kind of like the first few steps of that, right? Suppose that you've got x at t equals 0. X at t equals 0, let me write it down. So then, you know what x dot is at t equals 0? Because it's just m times x at t equals 0, right? Following that equation, because we had x dot equals mx. And this covers all time.
Yeah.
So then you'd say, oh, x at t plus delta t, this is the Euler rule, is x at 0. I'm missing out the t equals. Okay, just for brevity, this means that t equals 0. Plus delta t, that's the parameter that is your choice,
Right.
times
Yeah.
m times.
I guess I've just forgotten the relation because we just went to the x dot thing, so I've forgotten the relation from last week.
Sure.
Before Thanksgiving.
Yeah, so
Yeah.
when I was talking about it, I was ignoring or not considering the numerical part. This is considered the numerical part.
Right.
So if you follow that recipe, if you start at some point, you're going to be able to find what the next one is, what the next one is, what the next one is, and so on. You're going to be able to trace whatever dynamics. A separate issue was, can we write it out analytically, right? This was the numerical one. This is the one where we step through these small delta t guesses. But analytically, can we write down a function that says x of t is so and so? And what we saw is that when we have not the matrix equation, but the scalar equation, so not this matrix equation, but this scalar equivalent, x dot equals alpha x, that one we said, oh, that one we can write down analytically.
Oh, right.
So when we diagonalize, we can actually write in the new basis.
And that's the key thing.
Uh,
When you diagonalize, so you start with x dot equals mx, but after diagonalization,
can do x prime.
you now are at x prime dot equals the diagonal matrix times x prime, which means that you've broken it into a bunch of equations that look like this one.
equations, yeah.
You
And so
can-
now on each and now each one we can do analytic because now each one is a
you have a
simple
new
one.
basis.
And that's why we can say, oh, and the values alpha for each one are going to be the eigenvalues. And that's why we say, oh, if the eigenvalue has a positive real part, we know that it's going to blow up. Because we can write this down and we know it's going to blow up.
Oh, now everything makes sense.
Cool.
So that was a super key part. So we're getting to, but that's exactly right. That's the whole point.
Yeah.
Right,
That's
so
the
we
whole
did
point.
linear algebra in order to be able to diagonalize. What's so important about diagonalizing that when we have dynamical systems like this one, it allows you to break things down into separate scalar equations. And then you know the analytical solution, the properties of the analytical solution are straightforward, and so on and so on.
Can you explain again what x dot prime x prime and how that has to do with the eigenvalues and conflicts?
Yes. So let's maybe I'll do it on the other side so we don't erase this. So we started with this, right? So we start with x dot is mx, where these are in n dimensions. But we said, oh, I know that my matrix M, I can always write it like this. In some of the notes here, instead of this d, we have a lambda, but this is a diagonal matrix, right? The one that has zeros and all the octets. So this we know from linear algebra, right? So this was the guy where the columns are the eigenvectors. And Rebecca was asking, what do we do with those? Hear about that for a second. And this is the diagonal matrix. And this is the guy where its diagonal elements are the eigenvalues. And that all came from that initial MVI equals lambda I VI equation, the basic eigenvalue. So this diagonal guy, let's write it as alpha 1. Let's say that we were doing it in 3 dimensions, alpha 2, that looked like something like that. And alpha 1, alpha 2, alpha 3 are the eigenvalues of the matrix M. Yeah. Okay. So there, we're actually done. That's all we need. All we needed was to remember this basic eigenvalue correlation. Because now we can come back here and say, oh, well, this equation, let's multiply on the right by E V inverse. So that tells us that M is equal to E V inverse. So that says, well, you can write this guy, instead of M, let's write V inverse. And now let's multiply on the left by V inverse. So we get V inverse x dot is V times V inverse x. And that's the relationship that we wanted, because this transformation multiplying by v, on the left by the inverse of v, that's the transformation that says, oh, you're rewriting x, but now using the eigenvectors as the basis. So you
That's our x prime.
or it's, yeah,
That's what we call
Somewhere-
x prime.
somewhere in your notes, there was a story of, if you want to change to a new basis, you put the basis vectors as the columns of the matrix, and then you take the original vector and you multiply on the left by the inverse of that. So we're going to define our new coordinates as prime as the inverse of v and the original coordinates. And because v has its columns as its eigenvectors, that's what tells us, oh, what we're saying is that now we're describing x prime in terms of the eigenvectors of n.
Is that X or X dot?
Right here, this is x. So original coordinates. It's a great question.
X dot would also apply.
And this is the new coordinates. And the new coordinates is indicated by the prime. And now let's take the time derivative of this equation. So if we take the time derivative of that equation, on the left we get x dot prime. And on the right, well, these are all constants. So, in the same way that if you say, oh, I'm going to take mx, and I'm going to take the derivative of that, what you get is mx dot. And the same thing here, so we just get v inverse times x dot. Okay. And now you can see this guy, v inverse times x dot, that's this guy. So this becomes x dot prime is equals to d, the diagonal matrix, times v inverse x. V inverse x, that's the same as x prime. And that's the diagonalized version of the dynamics. So this equation is the same as this equation. These two guys are describing exactly the same dynamics. This one is describing it in the original coordinates. This one is describing it in the eigenvector basis coordinates. But they're exactly the same dynamics. Same thing. And when you guys run that side-by-side function, which is one of the exercises, that's what it's showing. It's showing the same dynamics on the left, in this space, on the right, in that space. And the main point about using this space, the diagonalized dynamics, is that now, if we look coordinate by coordinate, what we get is that x1, the first coordinate, I'm not doing, this is a scalar, so x1 is x1 prime, so the first coordinate of this vector is alpha 1 times x1 prime. The second coordinate, x2 dot prime, is alpha 2 times x2 dot prime. The third one, alpha 3 times x3 prime. Because this matrix is diagonal, and here it is, it's these dynamics that have things that mixed. So the first coordinate might affect the second coordinate, might affect the fifth coordinate. These dynamics have now been rewritten just by looking at exactly the same dynamics, but now in the eigenvector basis have been rewritten into a set of totally separate scalar equations. What's the solution for each of these? We know. So for example, that first one says x1 prime is going to be its value of 0 times e to the alpha 1. And so that's why looking at the eigenvalues told us, are we going to have oscillations? Are things going to blow up? Is the fixed point going to be stable?
Along those specific axes.
Yes, you're looking along each specific axis. For a fixed point to be stable, it has to be stable along all the axes. And that was the argument at the saddle point. And the saddle, you can be stable along kind of like the front and the back of the horse, but eventually you're going to roll off one of the legs. You're going to be stable in every direction.
This might be what you just said, but if we have all these separate alphas for a multidimensional thing, how do we take those numbers and we're talking about dynamics of the whole system?
So you do, that whole set of alphas is the full description of the system.
Okay.
And it's the full description of the system in eigenvector basis, but you know how to go back and forth.
Right, but like, say one alpha is negative and one is positive. And those means each other.
So you know then along the axis corresponding to the positive eigenvalue, which is specified, you'd move away from 0.
Okay.
And along the axis that corresponds to the negative eigenvalue.
So following what Steven said, if the real part of all the alphas is negative, then along every direction you're flowing back to 0, it's a stable point. If the real part of some of the alphas is negative and of some of the alphas is positive, then it's a saddle. Right? In 2 dimensions, it's literally a saddle, and in n dimensions, you can have 5 positive, 5 negative. It's kind of like a 10-dimensional saddle. But it's still essentially
You're right in pointing out that like the terminology you developed really kind of makes sense in 2 dimensions. And then when we go to more dimensional, we say, well, even 1 state, we'll call it unstable because it'll move away along that direction. You can look along each direction and figure out what's happening.
So these are great questions, because yes, these are kind of like the key points, and if we haven't gotten those across, it's fantastic that you guys are asking us this. These are the key questions.
One other thing I want to point out, because I think it comes up in your problem set, if this alpha is imaginary, we remember the famous equation, the Euler equation, where we had a 2 pi up here, and we knew that for different values of the imaginary number, I go around a circle. So you can specify also the period, or how fast the oscillation cycles when you have this representation. Because you can figure out how long I can progress in t to get to the next 2 pi iteration. Because of that e to the I, so if this is imaginary, e to the 2 pi I, so different values of I cause this to go around in a circle, and as I progress through t, I'm also going around in that circle, and when I get to intervals of 2 pi, I've made a full cycle, and however much t that took was how long my period is, how long each cycle takes.
We were asked this by the analytical solution, are we just supposed to rely on us knowing that relationship?
The analytical solution is the process we've just gone through. So yes, you're supposed to rely on knowing this solution and being able to do the diagonalization, should you need to. If it's already diagonal, you don't have to worry about it.
There's a bunch of equations for which analytical solutions exist. In this course, the only one we're asking you to know is x dot equals alpha.
Yeah.
And what's the analytical solution to that, which is that. And I was emphasizing that these are great questions, partly by way of encouraging people to ask more questions if they have. It's a great thing to do. So the next 2 weeks, not, I guess today's Thursday, so the next Tuesday, Thursday, the next 4 lectures are a topic that we're going to get into a neuroscience problem, we're going to get into decision making, we think it'll be fun. We're going to be doing a little bit of new math for probability, but not all that much new math. Really, we're going to be kind of like using what we've done here. So we think it'll be really fun, but it also means that we have a little bit of leeway to squeeze things. So you shouldn't hesitate to ask questions. We can squeeze a lecture out of those 4 to make sure that you guys are understanding all the basic material. So don't hesitate.
Then the next module, is this module not this weekend, but the following weekend?
Module test.
We need the module test.
Yes.
I don't think we've fixed exactly the date, but we're going to leave enough time to make sure that you guys have labs and go over and so on. And I don't know if we have decided yet, but the final one, so there's going to be a final test for what we covered in the last 2 weeks, and that's not going to be due until well after the holiday. So you guys can go home, rest, come back, and then work on it after you come back. Cool.
That is just a notational choice.
So
We're
it's not
not
like derivative, right?
No, sorry. Yeah, I made that mistake last time. Sometimes in physics, we'll denote a prime as a derivative. In this case, we are not. I could have called it. Okay, great. That was great. Okay, so now we can go. We kind of went through all this. Oh, we actually didn't talk about this terminology too much. So to remind you, when we have a two-dimensional system, if we want the fixed points of the system are the points where the derivatives are all zero. We remember that terminology. I also introduced new terminology called null climbs, which is if I set one of the derivatives of the variables equal to zero, I'll get some sort of line, and that we call a null climb. So one null climb corresponds to each time evolving variable in the system, because I can set each of these equal to zero, and then get a line out. And we'll go through examples of that, and I'm going to go through a simple example of that too. And we also know that, like we just said, the eigenvalues of the fixed point describe the nature of the fixed point. Which axes go to infinity, which axes go to zero, which axes rotate. Okay, for nonlinear systems, we can still actually find fixed points because we can set our equations, even if our equations do not obey this simple mx representation, but have some functional form that's very complicated. I can still say, hey, let's say my derivative's equal to zero, and then solve for a relationship between the variables here. And we're going to go through some examples of that too, if that's not clear. But I'm still able to set all my derivatives equal to zero. It doesn't matter how complicated my function is, even if it's nonlinear. And I can find the solutions to that zero. I can find the points in space, the different values of x, y, z, whatever, such that the derivatives of all of them are equal to zero, or the derivatives of only one of those variables is equal to zero. If I'm searching for, say, a null point or a fixed point. Great, null climbs often have different shapes. Okay, today we're going to talk about these nonlinear systems and how we can do a little trick to pretend that the fixed points in nonlinear systems are linear. Okay, that's called linearization. We're introducing that concept today. It's probably the final main concept of this module. And this works by finding fixed points in nonlinear systems and doing a bit of an approximation and rewriting that fixed point in a nonlinear system into this form, the linear form, or have a matrix. We'll tell you guys how to do that. Okay? And actually, by doing that, we can describe nonlinear systems in a very powerful way. And so when we can describe linear systems in a powerful way, because we develop all these tools and we can use them to describe nonlinear systems, we can explore now really complicated models that have, different relationships. And we're going to go through one of the more famous versions of that model first. And then also, if there's time, I don't know if there will be time, we're going to talk about bifurcations, and that's how fixed points change as parameters of a model change, and I'll explain that later if we get to it. But let's focus on linearization around a fixed point for now. Okay. So this is a famous model. I'm actually not really sure how you pronounce this. Loc-T-Volterra model. It's called the predator-prey model. It's a very simple nonlinear model, nonlinear dynamic model. And it's two variables. It's easy to track two variables. So we say that the variable of how something changes in time, one of the variables is some function of both x and y. And how the other thing changes in time is another function of both x and y. If these functions were linear functions, I would be able to write my system like this, and I would be able to do all the tools we just recapped. If these functions are nonlinear functions, we can start out by finding the fixed points and the null points. Okay? So this is what the model looks like. This is called a predator-prey model. Because you can imagine x is some prey, so maybe it's like a bunny, and y, or a population. This is like a population model. So we imagine x is some population of bunnies, and y is some population of, say, wolves. Okay? And the wolves eat the bunnies, and if the wolves are not present, the bunnies proliferate. Okay? So actually, that sort of conceptually is written in these equations. So x is how my population of bunnies changes in time. In the absence of y, wolves, x grows. When y is present, provided that y can feed on enough x, so there's a multiplicative term there, the bunnies are eaten, so they decay. Similarly, my population of wolves grows if there are wolves present eating existing bunnies. If there are no bunnies in the population, say the wolves have eaten too many of them, y decays. That's that negative delta y. Okay, so this is probably the simplest model you can come up with of these competing variables. That as one grows, the other squashes, and as the other is squashed, the one grows. Similar to actually the model we talked about on Tuesday. Okay, but it's a nonlinear system. I actually can't take this and write it in this form because of the fact that there's an xy and an xy in the off-diagonal terms. Okay, so what do we do?
Wait, could you just quickly go through what the constants
Oh, sorry, yes. So this,
the growth rate of the rabbits?
yes, perfect. So we also have constants in this model. Those are free parameters in the model. If I'm using that terminology and you guys are unclear, I'm going to call those guys parameters, all the Greek letters in that model. And they just refer to the scaling of all of the properties I just talked about. So you can think of alpha as like the proliferation rate, delta is like how fast the wolves die off in the absence of food, for example, and beta and gamma something like the consumption rates of this system. Okay, so they can be any numbers, and they're free to change. So when we look at there. So we can find the fixed points of this model doing our simple procedure. We set these derivatives equal to 0, and we solve. Right? Very straightforward. This is 2 equations and 2 unknowns. I can rewrite and get a solution for x and y in terms of these parameters, in terms of these proliferation rates, decay rates, etc. So let's do that. It's pretty straightforward. I set each of these guys equal to 0. And I can pull out the x from the top, I can pull out the y from the bottom. And because of the fact that x was in both terms in the top, I know that x equals 0, x is not going to move. I know that y equals 0, y is not going to move. So one of the fixed points is when both of these values are equal to 0. Neither will have a derivative. Is that clear? Let's go back to this. X dot's equal to ax minus beta xy, alpha x minus beta xy. If x and y are both 0, x dot doesn't move. Population stays at 0. Same thing with the y, the foxes. The other solution to this is, of course, setting that term in the parentheses equal to 0, solving, and I get a horizontal line in one case and a vertical line in the other. Actually, that x equals 0 and y equals 0. Oh, sorry. I'm still talking about fixed points. I get a solution, a particular value of x and a particular value of y, such that the entire system's derivatives are equal to 0, and that's going to be at these ratios of these parameters. 2 points in this system, such that if I am at those values, my populations of bunnies and foxes do not change in time. They remain constant. 2 fixed points. This is actually, in a fundamental way, different. Well, no, sorry. Yeah, in this case, we have multiple fixed points. 2 solutions to where this derivative is equal to 0. Different than in the linear cases. In the cases you come up with, you have single fixed points. Yeah.
So only when x and y equals 0, the scalars that were used in y now describe x and vice versa?
That's a good point. So, the value y for which it does not move is specified by the parameters alpha and beta in S, yes. So describe is not necessary. So you're right, I think. But in the case of the differential equations, how things were evolving in time, you're right. For y, we're governed by gamma and delta. But the fixed point of y is actually specified as the functions of wait, is that right? X equals 0. Yeah. Because x equals 0, that second term. So it might have made sense to introduce these in a different way. But if we want the first term, let's say the top term here, alpha minus beta y, we set that equal to 0, and we have a relationship for y. Right? We have y as a function of those parameters. So you're right, it's a little tricky. In the initial instance, I'm talking about how x evolves in time, and I use those parameters, alpha and beta. But then I just gave you a line with y and alpha and beta in it. That's because when x equals 0, y has a particular value. Then the derivative of x equals 0, y has a particular value. Okay? And when the derivative of y equals 0, x has a particular value.
So it's kind of like we're going to be at that point.
That's correct. That's exactly correct. Good question. Good question. Okay. So we can actually do conceptually an incredibly similar thing, but instead of figuring out where both of the derivatives equal to 0, I'm only going to be concerned where one of the derivatives is equal to 0. And we call those null clines. So I'm no longer interested in the case where both f of x and y and g of xy are equal to 0. I'm going to treat each one separately for just one moment. If I consider these in isolation, I will have lines describing each of these derivatives. It's essentially the same map as we saw before, but now I'm just having you consider them in different ways. There's nothing really tricky here. I hope this isn't confusing you guys. In the initial instance, we figured out where's the derivative of both x and y equals 0, and we found two solutions to that. In this case, I'm saying, where's the derivative of x just equal to 0? Well, it turns out the derivative of x is equal to 0 when x equals 0 and when y equals alpha over beta. In both of those situations, x is not changing. Along all of those points, two full lines of all real numbers. Same thing for y. The derivative of y does not change at all when y is 0 or when x is the ratio of those parameters. So now that we have these descriptions, we can actually plot what this looks like. So I'm going to choose some values for my parameters. And those are the values I'm choosing up top. Sort of an arbitrary choice. You can think of that as an arbitrary choice. And I have a system that looks like this. So the y null clines here are described by lines indicated in red. And the x null clines here are described by lines indicated in green. Where the green and the red intersect are the fixed points. Because those are the places where both y doesn't change and where x doesn't change. Cool? So I have this overlaid on a quiver plot, and you can see actually the value of the derivatives in x and y at every point in space. You can actually see something interesting about these solutions if you look at the arrows very carefully. It looks like these fixed points have different dynamical behavior around them. In fact, it looks like this bottom left fixed point, it looks like these arrows are going in along this x null cline, and they're going away along that y null cline, that bottom red line. Right? So one of those maybe is a stable along that line. Well, actually, you can probably call that whole thing unstable. But one of those maybe has a negative eigenvalue associated with it, and one of those maybe has a positive eigenvalue associated with But we have this other intersection point, but it's doing something different. It looks like the arrows are spiraling around. So that fixed point has sort of a different type of behavior, and it looks to be like it's oscillatory. So the goal of linearization is to be able to take a system like this and not have to plot a quiver plot, but actually figure out, using the tools we talked about in the first part of the lecture, how we can look at those fixed points and figure out what the behavior of the dynamics is around that fixed point. Cool? So how do we do that? Well, the idea here in this nonlinear system is to zoom in to each fixed point and pretend it's a linear system. So imagine I am just doing an approximation of my function around there, and that approximation doesn't contain any high order terms. It doesn't contain any squares. It doesn't contain any x times y's. It contains only linear terms. And if I can find that description, that linear description, pretending I'm only dealing with a small box around, is there? Yeah, pretending I'm dealing only with a small box around that intersection point, I've got something that looks a lot like the exercise sets in the problems we've done before. Linear system. Yes. Yes. The arrow, so this arrow, these sets of arrows, again, I've been calling them quiver plots, but they describe the dynamics or the evolution. Actually, I think I can do this better by showing you an example in Julia. So, let's do this model that I just described. This is the model here. Alpha times x minus beta times xy. That's describing my changing of x in time. My changing of y in time is described by gamma xy minus delta y. Okay, so I'm going to set those, and I'm going to plot those null lines. Let's hope this works. Fingers crossed. Still running. Still running? No. There we go. Oops. Let's ignore that. Hope nothing bad happens. So here's my quiver plot plotted in Julia. What I can actually do now is specify a particular point in space and evolve using the Euler method in time, because I still have a description of the derivative, and I can still do that dt trick. Okay, even though those derivatives are nonlinear. So I select a particular point in space, and I step along in time, and let's hope this doesn't take forever to load. I'm starting, oh no. Euler illustrate is not defined yet. Let's define it. Now let's try to run it. Starting at a point here, and I'm evolving in time along those arrows. Those arrows you can think of as wind blowing my differential solution through a field. You can see here, if I start at that particular point, I specified it as 0.4, comma 0.3, you can see up there.
Did that answer your question as to what the arrows are?
So the arrows are meant to be a visual illustration of how all of the solutions would move in time if I was starting at that.
So Stephen, at each point, how do you decide?
Yeah, so at each point, I have a derivative value associated with how much I'm going to move along the x direction and how much I'm going to move along the y direction. So I'm going to move a lot along the x direction. My arrows are going to be mostly pointed to the right if I'm moving, say, positive in the x direction. If I'm going to be moving a lot along the y direction, my arrows will be vertical. And if it's pointing upward, I'm going to be mostly increasing in y. So if I start at a particular point, and I follow sort of along the arrows in this map, I'm describing my dynamics in time, and at each point on the map, the arrow is defined by the derivative of x and the derivative of y, taking sort of a This is going to be something like x dot at a particular point. Let's call it A. How much I move in this direction. And then the value y dot at a particular point A. How much I move in this direction. And then all I'm plotting is the net vector addition of those two. If I move in this direction, positive, and this direction, negative, my quiver arrow will be represented as moving to the right and moving up.
So each layer of arrows like different dimension.
Each specified arrow is just a particular point in x and a particular point in y. So, sorry, I should have said like,
So the equations that we're starting from are, if we know our vector x, we know our vector x dot. So those vectors right now are composed of two coordinates, x and y. So that means if we know our position, x and y, we know x dot and y dot. Like those were the Lotka-Volterra equations. So now for each position in that plane, knowing where the position is knowing x and y, you know x dot and y dot. So the base of the arrow is the position, and then x dot y dot, that's the vector of x dot y dot.
makes sense.
The arrows representing derivatives with different dimensions.
And it literally means the direction in which the system would be moving if you're at that position. And the length of the arrow literally means the speed with which you're moving when you're at that position.
Makes sense? Cool. Come on, keyboard. Okay, great. So now I want to figure out how I can look at those fixed points in nonlinear systems and linearize them, or describe locally what the dynamics are. So here's how we do it. First, I want to remind you guys of the Taylor expansion formula. The Taylor expansion was a way for, and this was say, function of a single variable x, a single scalar x. The Taylor expansion was a way to approximate that function. So we approximated that function by using, by expanding it by its derivatives. This was the Taylor expansion. You guys have seen this before. Okay? So if I'm only interested, so if I want to specify x at some point away from x, say delta x away, I can think of this as composed of x at a particular value plus the derivatives of as I'm continuing to higher and higher order. The more derivatives I include, the more useful of a function of x I can get. So what I really am interested in, if I want to do a linear approximation to the function, is simply the slope of the line as I've indicated in red here. So it doesn't matter how complicated my function is, if I use the first derivative term, I'm approximating that function to a linear degree, and I'm basically just looking at its slope. So if I don't care about what the function does beyond its linear behavior, all of the curves, etc., I'm only interested in its linear behavior. I'm only worried about basically the first term. And in the case of, this is the introduction of a new term for you guys, in the case of doing this not for a single scalar variable, but for a high-dimensional vector, instead of worrying about just the first derivative, I worry about the analog linear algebra form of the first derivative. Okay? Remember, we talked about something like variance, and then I said, there's an analog linear algebra version of variance, and we called it the covariance matrix. I'm going to do the same thing here. There's an analog first derivative of a scalar function in linear algebra. It has a fancy name, and it is also a matrix. It's called the Jacobian. Okay? Some people are nodding yes, maybe some of you have seen this before. I'm noting that by J here. So all I'm saying for right now is we all know how to linearly approximate a function at a particular point. We calculate its first derivative. That's for scalar functions. But of course, we're interested in a linear approximation in a higher number of dimensions. And so instead of using a first derivative that we're all comfortable with, I'm introducing a linear algebra form of the first derivative and calling it a Jacobian matrix, designating it by J. I'm defining that Jacobian matrix almost conceptually the same way I introduced covariance matrix to you guys. If I have x as some function I'm calling f, and it's of x and y, the derivative of x is some function I'm calling f of x and y, the Jacobian, the analog first derivative of this two-variable system is going to be the derivative of the function f of xy with respect to x. Some of you maybe haven't seen this before. Instead of writing the derivative with a d, I'm writing it with a sort of reverse 6. That's a partial derivative. Has anybody not seen who has seen a partial derivatives before? Yes? Okay. Many of you have seen partial derivatives before. But for those of you that haven't, all I'm saying is I'm taking that function f of xy, and I'm going to derive it with respect to x, and I'm going to pretend y is a constant. And I'm going to do the opposite for the other equation. Okay? So this linear approximation to a function, this analog first derivative for a two-valued function, a function that takes in x and y, is going to be the derivative of this first function with respect to x, and then with respect to y. I'm going to put that in the first row, and then in the second row, it's the derivative of this function of y with respect to x, and then with respect to y. Right? So this is actually conceptually quite similar to the covariance matrix. Right? Along the diagonals, I've got the function of x with respect to x, and the function of y with respect to y, and along the off diagonals, I have x with respect to y, and y with respect to x. Okay? Because this guy describes the changing of x in time, and this guy describes the changing of y in time. I'm going to pause for a moment, because this is potentially the most challenging part of today. So what I've done is I've told you that you guys know how to calculate first derivatives of scalar functions. But we're talking about functions of two variables here. And we're talking about describing a two-variable system, x and y. The linear approximation to that is not just simply calculating a first derivative. It's calculating all of the pairs of the derivatives of the two variables and making a matrix out of it, in the same way that covariance matrix describes all of the relationships between variables and variance.
Could you maybe give like a simple example of
Yeah, of course. I mean, the simplest example, well, I mean, we'll go through it, but I can just. So if I have f of x and y equals 2xy, if I'm taking the derivative of this with respect to y, it's going to be 2x. So let's write it out for completion. D of f of xy dy equals 2x. Okay, and d of f of xy dx equals what? 2y. You got it. We're not going to do with real complicated derivatives here. You can't even read this. Sorry. I hope my words. Yeah. Okay. So if we write a matrix like this, we now have a local linear description of the system. This matrix is 2 by 2. And we can use all the tools we had before. Basically, we can take our system and describe it as a locally acting this right here, where our m is our Jacobian. And we're saying it's local because it only applies at the fixed point, or at a particular point. In this case, I'm going to say at the fixed point. At the particular point, we linearize around, right? I made my assumption here. This nonlinear guy is only linear at a particular point. At a new point in space, it might have a different line to describe it. So by locally describing a function as linear, I'm simply saying at a particular two-dimensional point, this is the plane describing its two-dimensional dynamics. And it's going to be the linear description. Okay? So we can, this might also illustrate itself more clearly when we actually just do this. So this is taking that model and performing those partial derivatives. Okay, so let's step through what I have on the board. I don't have, so my f is that alpha x minus beta xy. And my g is that gamma xy minus delta y. Okay? And I'm saying a local description is going to be the derivative of the f with respect to x, then the derivative of f with respect to y, derivative of g with respect to x, and g with respect to y. So let's go through that. Top left of the bottom right matrix is alpha minus beta y. That was the derivative of alpha x minus beta xy with respect to x. All I did was drop the x, right? The same thing with respect to y. All I do is drop the x's, I get negative, all I do is drop the y's, I get negative beta y. Does that make sense? People okay with this? Local linear description of the system? Yeah.
But why are you going to explain why the Jacobian ends up describing the dynamics locally?
So the Jacobian describes the dynamics locally because it is an approximation of the whole function linearly. So in the same way that this line describes that function locally, right? If I'm at that point indicated in red, and I move slightly to the left, I increase by a certain amount, and I move slightly to the right, I decrease by a certain amount. So the local description of that function is described by that line. So as I move to the left, I've got good guesses of my next values. I'm saying the case is here that we can do the same thing in multiple dimensions, but our analog derivative is this Jacobian. So as I move around that point, I'm moving approximately correctly, only I'm doing so in a linear way, as opposed to potentially not.
Why is it like the partial?
So why is the Jacobian a linear description of a high-dimensional system? I don't know. Carlos, you have a good intuition here?
Write out the Taylor expansion.
Yeah, so there's a, I'm not going to do this off the top of my head. You can write out the Taylor expansion of each individual piece. And so I'll get them, like if I consider y a constant, just for the sake of the top left, let's consider y a constant. I've got a function of x, right? So what's my movement in that direction? Well, it's the same thing as the first derivative with respect to x. If I consider x a constant and do the same thing with y, I'm moving in the other direction and I'm approximating that line in the other direction. Right? And if I do the off diagonals, I'm pretending that my function x, I'm seeing how my function x changes along y, and I'm seeing how much my function y changes along x, and I'm doing so in my. So basically, because x is two-dimensional, I'm thinking, because the description of how x changes in time is two-dimensional, it changes a little bit along the x direction and it changes a little bit along the y direction. What I'm saying is for this first column, this first row, I'm figuring out what's the linear amount x changes along the x direction and what's the linear amount x changes along the y direction.
X changes along the y direction.
Yes.
Oh, if you were to
Right?
drop one, then
So both x change, where's the, Do I have the? There we go. X changes along as a function of x and as a function of y,
Yeah.
right? And y changes as a function of x and as a function of y. So all I'm doing is I'm assembling a matrix and saying, what's the linear approximation to x changing along the x direction and to x changing along the y direction? And what's the linear approximation to y changing along the x direction? And by making that linear description, I have a full linear description of how both of them change as I step along in each direction. And I could do a Taylor expansion for each one of those, treating either x and y as constants. And either Taylor expanding f or Taylor expanding g. Okay? Okay, so let's just do that. Oh, actually, I think we did this right. So this was clear how you actually did the calculation, how you made those linear approximations of each function along each direction. And now I can look at what's happening at each fixed point. So at each fixed point, I had a particular value of x that I solved for, and a particular value of y that I solved for. I did it before. One of those was 0, 0. So I can look at my matrix here, and I'm just going to tell you we could take that matrix. That's a local linear description. It's a local M. The system is locally described in this way. So I can take this matrix just like we did before, and I can look at its eigenvalues. And if this is the eigenvalue of this solution. So I can take M and plug this into Julia for a particular value of A and a particular value of negative delta, get out some eigenvalues. One will be positive, one will be negative.
So in that case, are you asking essentially like how much does x change as you take one step in the direction of one of the eigenvectors? After you've diagnosed them?
So for this particular fixed point, so there were two fixed points, right? There were two places where the multiplies cross. And what Stephen is writing down there is what's that J matrix which corresponds to our matrix M at the fixed point y equals 0, x equals 0. And it turns out that that matrix, that linearization, that corresponds to the matrix M, in this case is already diagonal.
It's already diagonal, so those are the eigenvalues. Yeah, I mean, let's do it. We can do it for the other fixed point.
So because it's already diagonal, the elements on the diagonal are the eigenvalues. You don't need to go to diagonal.
But so you're right in pointing out that along the x direction, I'll be moving with a positive eigenvalue. It will explode, and along the y direction, it will converge. I hope that's actually, there wasn't some sign flip I'm missing. Wait, where's the, man. So I got my eigenvalues out, right? One was positive and one was negative. What does that mean? It means I'm at a saddle point. That's exactly what we have at 0, 0. I'm decaying in the y, and I'm decaying out in the x. So that is what we have. So you're exactly right in the point. Now the other fixed point, which we had found as being those ratios of the parameters, if I look at the eigenvalues of that matrix, so the local linear behavior at that point, I now get eigenvalues that are imaginary. Okay? So I had a nonlinear system that had two fixed points. One of the fixed points, we linearize the system. We figure out, at one of the fixed points, what does my local linear behavior look like? It looks like I'm exploding along one direction and decaying along another. That's exactly what the solution looks like. At the other fixed point, what does my local linear behavior look like? Looks like I'm oscillating. Those eigenvalues are imaginary. Okay? So I had a system, a full system, I calculate the derivatives, and then I can actually plug in for different values of y and x what that local linear behavior will be. So this is our key to understanding nonlinear systems. Linearize the whole system, pick particular points, and look at what that local linear behavior looks like.
Will the eigenvalues when you're at the zeros fixed point always be saddled?
In this model, well, that's a really good question. No. Well, I guess, why do you ask that question? It's a very interesting question.
I guess I asked if I was wondering, but I guess if you, like, let's say that delta in this case is a negative,
Perfect.
then it
Yes.
would be something.
Yes, exactly. That's exactly right. So depending on the parameters of my model, this can change. And you can download the code, because I have the code for this, and you can actually play with these numbers. All you have to do is change, like, literally one number in the code. You can plot a new set of null lines, and you can see, did my fixed points change in the sensible ways. And in fact, we're not going to have too much time to go into it, because there's only 10 minutes left, and there's a whole other, well, we'll see, but maybe I'll just skip to that. But there's a sort of whole literature on describing how fixed points change as I change parameters. Exactly what we point out. And that is called bifurcations. When a fixed point changes, when a parameter of a model changes the nature of a fixed point solution, maybe it moves from stable to unstable, maybe it moves from nothing to oscillating, or fixed to oscillating, etc., that's called a bifurcation. And sort of each one of those things has a different name for its bifurcation. We'll go through an example of that. Yeah.
So can you have, like, in one fixed point, if you have an eigenvalue that's real and one that's imaginary, and then also can the eigenvalues have real and imaginary components both in one eigenvalue, or is that just eigenvalues?
No, certainly an eigenvalue can have a real and imaginary component. That was what we were talking about when we spiral outward. Right? That means if I have a local linear dynamics that spiral out, it means I'm positive, real, and I have an imaginary component. Okay? If I am only imaginary, I oscillate, but I never spiral out or converge in. We can go through different examples of this, but yeah, I don't know what's best. We have 10 minutes left. Okay. I'm going to not do the mutual inhibition model. Let's save that for next week. Instead, I'm just going to show you guys pool plots. So let's first pause one more and say, are there any more questions about this process? Taking a nonlinear system, linearizing it by calculating its partial derivatives in a matrix to figure out how it linearly changes along each function linearly changes along each direction. Using that local linear solution to pretend my system behaves like this at particular points. It approximately behaves like this at particular points, and I can understand my fixed points by plugging in those fixed points in and thinking about it in this way that we've thought about it before, looking at the eigenvalues, for example, and describing the local dynamics. Okay. So let's get to bifurcations. I think that'll be cool. And if everything from here on out you're like totally lost, don't worry about it, because we're not going to test you on bifurcations. I think that's fair to say. You will not be tested on how fixed points change, but understanding bifurcations is how, if I had a really complicated model, look, the model we have is super simple, right? I went through actually a little bit more complicated model on Tuesday. The nonlinearity was a little bit more complicated, etc. Those derivatives were kind of hard to calculate. You could imagine, in fact, maybe some of you are familiar with the Hodgkin-Huxley equations. Some of you heard of that before? They're big, complicated equations that describe how the dynamics of calcium ions and sodium ions and potassium ions all change, and they have multiple differential equations to describe each of those features. How the hell do I understand a set of differential equations that's that complicated? Well, I can do these kinds of things. I can figure out local linear behavior at particular points, and I can figure out how, if I move one of the parameters in the Hodgkin-Huxley model, maybe I move the channel conductance of potassium or some property of a sodium channel, etc. And I can figure out how do the dynamics change as I move that parameter. That's called a bifurcation, and neuroscientists use those tools often in biophysical models to get a handle on what happens if I give you a drug, how do those neural oscillations change, etc., etc. Okay, so that's called a bifurcation, and it's exactly to your point of can eigenvalues change as I change parameters? Okay? So the simplest example of this, we're actually going to go back to one-dimensional, but nonlinear. Okay, this is my Greek. I think I've already said this. We want to see how fixed points change as a function of different parameter values. When fixed points are created, destroyed, or they change properties, say go from real to imaginary, we call those bifurcations. Okay? So here's a very simple kind of bifurcation. Let's imagine we have a derivative of a single scalar variable that's proportional to that how much that variable changes in time is proportional to that variable squared minus some constant. And that constant is a parameter. Okay? So for different values of alpha or of A, call it A, I can have different numbers of fixed points. Let's spell that out. So if A is -5, and I'm plotting my derivative of x in time as a function of x, it never crossed 0. So do I have any fixed points? No. If I move my alpha parameter to higher and higher values, I have descriptions of how this changed in time, analog moving this line down. And at some point I cross 0. As soon as that value of A for which I cross 0 occurs, boom, that's my bifurcation. Okay? And I went from a system with 0 fixed points to a system with instantaneously 1 fixed point, right when that touches for a very special value of A, and 0, right? And then as A goes positive, I have 2 fixed points. One of those fixed points is stable, because if I am below it, I increase, and if I'm above it, I decrease. And one of those is unstable, or the opposite reason. The creation of a stable and unstable fixed point from nothing is called a saddle node bifurcation. Why is it called a saddle node bifurcation? What do we know about saddle nodes? One of the eigenvalues is stable, positive, and one of those eigenvalues, well, stable, unstable, positive, one of those eigenvalues is stable, negative. Cool? So that's called a saddle node bifurcation. And sometimes we visualize this using a bifurcation diagram where I plot basically my fixed points as I change A. So when A is below 0, I don't have any fixed points, right? I move A, and as I increase A, this solid line indicates a stable fixed point. This dotted line indicates an unstable fixed point. I've created a stable and unstable fixed point. From nothing as I move A, we call it a saddle node bifurcation. Okay, we can show that because I spent the time to make this. Let's just show you. Okay, here's our saddle node bifurcation. All right, let's hope this runs. Great, so what I'm going to do is there's going to be a plot on the left and a plot on the right. The plot on the left is going to be that cone decreasing. The plot on the right is going to be how x moves in time. Okay? And as soon as that saddle goes below 0, I'm going to create 2 lines along x in time, null lines if you will, where x doesn't change. An unstable and a stable. So let's look at that. Hopefully this goes. Okay, so you can see here, this is the description. I'm moving this down, and as soon as it crosses 0, 2 null lines emerge along time. And those are the points in which x does not change in time. So this right plot is x over time. So it's either going to decrease over time, it's going to increase over time. And if it ever finds a special point such that it's not going to move, it's not going to increase or decrease, that's a fixed point. So what you saw here was the creation of two fixed points. Values for which x does not change in time from a system that initially had none. Let's watch it one more time, and then we can go. So there's no fixed points, no lines where x does not change in time, and then we create two instantaneously. One of those stable fixed points, because those arrows are, you can barely see it at the top, the arrows are moving away from that line. That's our unstable fixed point. And at the bottom, the arrows are moving towards that line, that's our stable fixed point. And the process by which this is created, as I very alpha is called a saddle node bifurcation. There's a bunch of bifurcations that I don't think we'll have time to go into, but this is probably the simplest one. Cool? Okay, that's it.